Okay, the second half of section 9.6 is talking about the root test. Last time we talked about the ratio test. What did the ratio test say? We had three conditions. We had three possibilities. What were they? A plus 1 over. Okay, if it's less than 1, yeah, converges absolutely. If the limit was bigger than 1, what did it tell us? And if the limit was equal to 1, yeah, inconclusive, do something else. This was the ratio test. Our root test is very similar to it. Question? Oh yeah, I was forgetting about this list. Okay, so that's our ratio test. What test do we have to test for absolute convergence now? The first one that we talked about was check the absolute value, the series of the absolute values for convergence. And then the second one that we're going to have now is the ratio test. We're going to add to that today the root test. These are all for checking for absolute convergence. When we actually put these all together, which is going to happen on Thursday, this is the last of our tests for convergence or divergence of a series. On Thursday, we're going to dump it all together and mix them all up, and we'll all be good and confused. But if you think about absolute convergence, these ones tell you absolute convergence. The other ones only tell you convergence or divergence. They don't tell you absolute convergence. So let's look at our root test. Our root test looks just like the ratio test, but instead of using the ratio an plus 1 over an, we're looking at the nth root of the absolute value of an. And the reason we take the absolute value is because you can't take roots of negative numbers. So we get rid of the minus sign and we do our nth root of an. If that limit is less than 1, then the series itself converges absolutely. If the limit is greater than 1, or it goes to infinity, then the series diverges. If it equals to 1, it's inconclusive. Try something else. So let's see why it works. And here again, we're going to compare it to a geometric series. So I'm going to look at the first case again. We're going to assume the limit as n goes to infinity. The nth root of the absolute value of an is less than 1. That means I'm going to say this limit, and I know it's going to be a positive value. It's going to be 0 or bigger because its absolute value is here. I'm going to call that limit r. And I know that that limit is going to be smaller than 1. So let's look and see what that means. I know that there has to be some number, I'm going to call it capital N, such that the nth root of an is going to be, I'm going to say less than or equal to r. The n plus 1 root, an plus 1, is less than or equal to r, and so on and so forth for all time. Notice what this means. If I multiply the nth power to both sides, then I get the absolute value of an is less than or equal to r to the n. Tell me about the absolute value of an plus 1. R to the n plus 1, and so forth. So if I'm looking at all of these terms, what that tells me is that the terms an plus j is going to go from 1 to infinity. All of these end terms right here, that summation has to be less than or equal to r to the n plus j. This is a geometric series. This converges by the geometric series if r is less than 1. Comparing it to a geometric series, this converges if r is less than 1. I switch the inequality if r is bigger than 1. So if my limit is bigger than 1 for the second case, right here I would have this r would be bigger than 1. And then down here, each of these values would be greater than or equal to. And I would come down here and I'd have bigger than the geometric series with r bigger than 1. But does a geometric series with r bigger than 1 converge or diverge? Diverges. So if r is bigger than 1, it diverges. If r is less than 1, it converges. The problem happens when r equals to 1. Because if I have it identically equal to 1 right here, I no longer have this inequality right here. I have to have a strict equals sign right there. And it doesn't always work. I need that inequality to do my comparison. That's why it works. So let's apply our test. Determine the convergence or divergence of this series, e to the 2n over n to the n. Notice that the root test is only used when n is in the exponent. That's important to write down. Root test is only used when n is in the exponent. Don't apply it any other time. It's very painful in all other times. So only use it when n is in the exponent. So do I have n in my exponents for this series? Yeah, it's in the exponent for both of them. So an is going to be e to the 2n over n to the n. That means I need to look at the nth root of the absolute value of an. That's going to be the nth root of the absolute value e to the 2n over n to the n. I would submit to you that I can drop the absolute values because there's no minus signs in there. Nothing is ever negative, so I'm going to drop the absolute values. Now, watch carefully. I'm going to group my exponents together and take that power n out. Now let's take our limit. Limit as n goes to infinity, the nth root of e squared over n raised to the n power. What happens to the nth root of everything raised to the n power? They cancel. So then we have the limit as n goes to infinity of e squared over n. What is that limit? 0. 0 is less than 1. So converges, and in fact it converges absolutely by the root test. I could say converges, or I could say converges absolutely. I don't need the absolutely on this one because I didn't have a minus sign, but it's not wrong to say that it converges absolutely. Any questions on that? Okay. Question?
So you can still use the ratio test on this too, right?
Yes, you could.
How do you know like
Whenever you have n in the exponent, it's easiest to use your root test. But if you don't have n in the exponent of everything, then your ratio test is easier. It needs to be in the exponent of everything. That is the only condition that you're going to use for the root test.
when you say everything, does that mean like numerator, denominator,
Yeah.
or
every term in the numerator and every term in the denominator. Because otherwise you have the nth root of something left over and you're putting n in the exponent. And then it's just like our 1 plus 1 over n to the n thing. You have to do y equals, take the natural log of both sides, and it becomes painful. Yeah. Any other questions on that? Okay, let's do another example. Oh, let's let you do an example and then I'll do another one. Notice yours has a negative sign in it. When you take the absolute value, that thing goes away. So you don't even have to worry about it. But I'm asking you to check for convergence or divergence. If it converges, tell me if it converges absolutely or conditionally. Make sure you tell me convergence absolutely, guys. And by the root test, I want to know what test you're using. Okay, does everybody have it done? Okay, so we're looking at this next one, determine the convergence or divergence of this series. Notice it's everything to the power n, so the root test is going to be the easiest here. An is going to be 6n plus 5 over 2n plus 1 raised to the power n. So let's take our limit. Now, I don't have any minus signs in this, so I can drop the absolute value. So that's what I'm going to do next. What happens to my exponents? The nth root and the n. They cancel. And so I get the limit as n goes to infinity, 6n plus 5 over 2n plus 1. If you guys are very comfortable with L'Hopital's rule, I'm going to show you doing the division instead of L'Hopital's rule. Oh, that was supposed to be infinity. This becomes a 6n over n. I'm dividing by the highest power in the denominator. So 6n over n plus 5 over n divided by 2n over n plus 1 over n. The n's are going to cancel in the first two terms. And where does 5 over n go as n goes to infinity? 0. So then what is my limit equal to? 6 over 2, which is, and 3, how does that compare to 1? Larger than 1. So the series itself does what? Diverges by root test. There's our answer. Series itself diverges by the root test. Now, if you compare that to the one you guys just did, other than that minus 1 to a power, which didn't affect it at all, what's the difference in it? I mean, it looks to be the same, other than the constants in front. Yeah, that constant in front is enough to change it from converging to diverging. So just because something looks like a form you would think would be convergent, our last example, doesn't mean it's necessarily going to converge. The ratio and the root tests are tests that allow you to check things that look very similar to each other, and some of them will converge and some of them will diverge, depending on what that limit is going to be. Any questions on that? Question? No. Just showing a different method of doing it. Everybody is very comfortable with L'Hopital, so I wanted to show the other method. You can use either one you want. Okay, this one we can approach several different ways, actually. There's an nth term test that we can use for this one. This one's going to diverge. We can use the root test, which is the one I'm going to use right now. Or you could even try and apply the ratio test. I'll show you the root test, and then I'll show you the nth term test, because I want you to see both of them. So, for the root test, I know an is going to be 1 plus 1 over n to the n. We take the limit as n goes to infinity of the nth root of 1 plus 1 over n raised to the n. What happens to my powers? They cancel. Now this is a very easy limit. What is that limit going to be equal to? Compare it. Bigger than 1, less than 1, equal to 1? Equal to 1, so inconclusive. When it's inconclusive, we go use a different test. I'm going to use the nth term test, and let me show you why. This limit we all know is going to be e to a power. So I'm going to call this y. If we take that limit, what do we do? Ln of both sides. What do we do with the n and the exponent? Bring it down in front. And then we're trying to use L'Hopital's rule in this case, so I have to make it into a fraction. So I'm going to take that n and put it in the denominator as 1 over n. Now, what happens to the numerator? As n goes to infinity, 1 over n goes to 0. So we get the natural log of 1, which is 0. And the denominator goes to 0. So apply L'Hopital's rule. So I get 1 over 1 plus 1 over n, derivative of the natural log, times the derivative of the inside, which is minus 1 over n squared. Derivative denominator is minus 1 over n squared. Does anything cancel? And so what do we get for our limit? Yeah, which equals to 1. All of that is equal to the natural log of y. So we have natural log of y is equal to 1. Y then is equal to e to the 1 or e. Now this was the limit of the inside of our series. E is definitely not equal to 0. So what does that tell us about this series using the nth term test? Diverges by the nth term test. The original series diverges by the nth term test. Original series diverges by the nth term test because the limit of what is inside is not equal to 0. It has to diverge. It's like adding e to itself an infinite number of times. That's going to be infinite in itself. Okay, sometimes your test is inconclusive. When it's inconclusive, it may or may not converge. You have to try something else. Last time we saw an inconclusive one with the ratio test, which did converge. This time I showed you a divergent series that was inconclusive using the root test. Just because something is inconclusive does not mean you can assume that it either converges or diverges. You have to try something else to know for sure. That's why we don't like inconclusive. Any questions on that? Okay. Let's look at this one. It says use the root test to determine the convergence or divergence of the series 1 over n squared. So what is an? 1 over n squared. By the way, what kind of series is this? P series. And p is bigger than 1, so it converges. When p is bigger than 1, it converges. So this one's going to converge, but let's do the root test on it and see why we wouldn't want to choose a root test for this one. By the way, don't write this one down in your notes. I don't want you to ever do this, so don't copy it. But we want to watch it and see what happens if we chose to do the root test on that. The nth root of 1 over n squared, I'm going to write it as 1 over, not 1/2, 1 over n, and that nth root part is going to be 2 over n. I think I can squeeze it in right there. Do you guys see that? Or did I skip too many steps? Some of you are looking at me kind of glassy-eyed. We write it 1 over n squared to the 1 over n, and then I can take that into 1 over n to the 2 over n, like that. I have this n in the exponent right here. I'm trying to take a limit. Whenever you have n in the exponent and you're trying to take the limit, you have to set it equal to y and take the natural log of both sides. So I'm going to have the natural log of y is equal to the limit as n goes to infinity, the natural log of 1 over n to the 2 over n. When you take the natural log of a fraction, it's like a subtraction. Becomes the natural log of 1 minus the natural log of n to the 2 over n. What is the natural log of 1? 0. So then this becomes the limit as n goes to infinity minus the natural log of n to the 2 over n. What should we do with our exponent right here? Out in front. I'm going to write that as minus 2 natural log of n over n. That minus 2 is a constant. It's the natural log of n over n that I'm worried about. Where does the natural log of n go as n goes to infinity? Infinity. Natural log is our family. The logarithmic functions is our family of slowest increasing functions. It does go to infinity, but it's the slowest one to go there. And then n goes to infinity, so apply L'Hopital's rule. I'm going to just leave the minus 2 out in front. What is the derivative of the natural log of n? 1 over n. Derivative of n? 1. Now as n goes to infinity, where does that go? 0. So our whole answer is going to be 0. That means the natural log of y is equal to 0. What does that tell you y is equal to? E to the 0 is 1. Now, that was our root up here. This nth root, the limit of the nth root, is equal to 1. So what does that tell you? Apply your root test. Yeah. That's why I told you guys not to write it down. What is your takeaway from this? Root test does not work for p-series. Yes. N is not in the exponent. Don't do a root test for a p-series. Only use the root test when n is in the exponent of everything. Or if your homework tells you to try it because they're forcing you to go through some pain and misery. But don't ever use the root test on a p-series. It's not going to work. It'll always give you 1. It will always be inconclusive. I know this series converges by the p-series test. Much simpler than going through that root test. Any questions on that? Okay, we are done for today. Make sure your names are on your papers and your papers are turned in. Make sure, guys, you bring your cheat sheets to class on Thursday, we're going to be talking about dumping all of our series together and trying to figure out some problems in class. So bring your cheat sheets to class on Thursday.